And now let's push even earlier, the really early universe. So our current understanding of fundamental physics is that there are four fundamental interactions: electromagnetism, the weak interaction, the strong interaction, and the gravity. And some time ago, electromagnetism and weak interaction were unified into electro-weak interaction by people like Glashow and Salam and Weinberg. And then the idea was like, well, at some point maybe there was unification between electro-weak and strong, that's so-called grand unified theories. And if you keep pushing, at some point maybe gravity was part of the whole thing. So essentially the idea is, as you go to ever higher energies, meaning deeper in the past, interactions become the same. Or rather, if you look forward in time, they split when energy drops beyond a certain limit. And so what used to be four different interactions, what used to be one interaction first splits into gravity and everything else, then that splits into strong nuclear force and electroweak, and that splits into weak and electromagnetism. That's pretty theoretical. We know one of them works, which is electroweak, but everything else is speculative. And this is very interesting because if we can say something about all this from cosmological observations, it probes physics beyond anything we can test in the lab. So what we call electroweak era is 10 to the minus 10 seconds after the Big Bang, roughly speaking. And at that time, temperature was 10 to 28 degrees Kelvin. We never make anything like this in stars or anything like that. At something like 10 to the 15 degrees Kelvin, quadrillion degrees, again, much more than anything in stars, electroweak splits together. And that's as far as we can go in accelerators today. Now, if you push this by another 25 orders of magnitude, then ostensibly there is this grand unified theory transition between that grand unified theory and strong force on one side and electroweak on the other. And that may be what's driving the inflation. We don't know it. In the meantime, something interesting happens. Now, if you look in the universe today, there is a lot more matter than antimatter. In fact, there is hardly any antimatter. And why would that be? Because in principle they're equivalent. There is no mass-energy difference. It's roughly speaking, one particle in 10 to the 9 or 10 to the 10 that is the difference. So if somehow in the early universe there was this tiny, tiny imbalance between matter and antimatter, they're all going to annihilate except for that one little excess. And the energy of the annihilation is what provides energy content to the universe. This is essentially what eventually becomes microbackground photons. But why? Why would there be this asymmetry? So as early as 1967, Andrei Sakharov proposed a mechanism that explains that, which goes way beyond this class, but essentially involves violation of some symmetries in particle physics, some of which are actually testable, others not yet, and departure of thermal equilibrium from equilibrium, which is provided by the expansion of the universe. And now people believe that Sakharov mechanisms is essentially why there is a symmetry between matter and antimatter. So just the fact that we're pretty sure that there isn't more antimatter than negligible amounts that we see because of the absence of gamma ray annihilation fronts and such is already telling us that this must have happened somehow in the early universe. And let me introduce so-called Planck units. Max Planck, at the end of 19th century, came up with a set of units asking, meters and centimeters and grams and seconds, they're all arbitrary. They're defined by some international body. And, right? Nature doesn't know anything about meters and seconds. And so how can you make units of time and length and mass and so on that are really natural units? And one thing suggests itself is to use various physical constants, such as speed of light, Planck constant, Newton's gravitational constant, and combine them in ways that yield length or time or mass or whatever. And so here they are. And useful thing to remember is that, well, roughly speaking, Planck length is 10 to the minus 33 centimeters. Planck time is roughly 10 to the minus 44 seconds, and Planck mass is roughly 10 to the minus 5 grams. So when the universe reaches densities that would correspond to, say, 1 Planck mass per cubic Planck length, which is around Planck time, for sure something interesting must be happening back then. We don't really know that this is the case, but it's a pretty good hint because those constants are there for some reason. And we think that roughly then gravity was unified with the other forces, just because when else could it do it? And how that happened? Well, we do not have believable theory of gravity yet. There are attempts to do this, the so-called M theory, which is generalization of the string theory. There are other cosmologies called epiriotic cosmology, there's string landscape, multiverse, and so on. All of that is extremely speculative and not tested and maybe a priori not testable by experiments. But eager minds do try. And so conceivably, this is what will really stimulate the next level of understanding in fundamental physics in the same sense that quantum mechanics and theory of relativity changed our fundamental understanding of physics.